Hi everyone. I'm Balint. I'm a PhD student at the Ritmo Center for Interdisciplinary Studies in Rhythm, Time, and Motion. That is to say, it's a center of excellence in the overlap of the Department of Musicology, Psychology, and Informatics. And some of you were visiting us in March. So it's great to now come here to where you are and meet more of you and honestly just get so much inspiration from watching and listening to your work. So I'm a PhD student and my project is about image sonification. Making sounds out of images, to say it very simply. And my kind of more focused research title is Perceptually Aligned Deep Image Sonification. And this title tries to pack everything in one sentence. So I'm gonna, in this talk, unpack this starting from the end and moving towards the first phrase. So let's start with what is sonification. If you're not familiar with it, it's basically making sound out of data, or the more technical definition is like transforming data relationships into perceived auditory relationships. And a really common paradigm of doing this is called parameter mapping sonification, where you have a data set of features that you care about. You have something that makes sound based on some input parameters. Let's call it a synth. And then you create a mapping between your data set of features to the input parameters of your synth. And then you listen to the output result, and based on that, try to infer something of that phenomenon that your data set of features represent. And so that's not all there is in sonification. That's, let's say, the most used paradigm in sonification. But let's move on. What is image sonification? Well, image sonification, when this data set of features comes from images, but then now there is, I feel like, a very obvious question about image sonification, which is why should we sonify something that we can already access with a sensory modality? I guess in general, the motivation of sonification is to make data accessible to your senses, and therefore for your pattern recognition machine in your head. So why should we do this if we can already see the data in a way? There can be many motivations for this. For example, the visual modality might not be equally available to everyone. Someone might need some degree of sensory substitution. It could also be that your visual attention must focus on some other task while you still want to monitor some process happening. I think I'm a little bit privileged because I'm working in a collaboration with biologists whom are actually using images and hopefully eventually sound as well for data exploration. So they are capturing a very fundamental biological process called autophagy. It's kind of like a natural self-cleaning, self-recycling process. And problems with autophagy are very much linked to problems with cancer and aging. So it has a huge impact understanding this. And they know they can capture this process in fluorescence microscopy, but then they end up with millions of images like this. And to my surprise, they are often actually just opening different images, maybe from different gene combinations, and just comparing them side by side, or flipping through a time series and just trying to get a sense of, in a way, with a qualitative engagement of what the data is. And so together we had this question at the start of my PhD, like, is there something maybe that would be easier to hear in this sea of data than to see? Or maybe more modestly, is there anything the sounding display can contribute to the understanding of this biological process? And so then I was thinking, oh, it would be so nice to have one little compact toolbox, preferably integrating in the already existing scientific computing ecosystem in Python to do this, to load images and then make sounds out of it in a reliably, or how should I say, in a reasonably simple way, and preferably in an interactive way. And so that's what Pixelsonics is. Some of you in the March visit already had the chance to wither through a long presentation and workshop on this. And I'm just gonna say, since then, the system has greatly improved, but basically it started out as an implementation of this parameter mapping sonification concept. So you have this clear role of feature extractors, I mean, image feature extractors, I should say, synths that turn parameters into waveforms, I guess, and then a mapping in between these things. And then where everything happens is the app, as in like the container for this pipeline, where you load an image, query it, and then there's this pipeline from features to mappers to synths. And then you can real-time interact with this. So just to get a very quick idea about this, first of all, you can already install this via your favorite package manager. And once you did, you can evaluate this pixelsonics-notebook command, and it will bring you to this thing, this ginormous and ever-growing Jupyter notebook, where I'm trying to entertain you and also yeah, get you into how to use the toolbox. So without further explanation, it feels like something like this, except I might need to... Oh, it's going to the Zoom audio device. So probably people on Zoom might hear it. Let's try the Core G2. And no, okay, it worked in the morning, but probably something happened with Zoom. So the idea is that you have this little stethoscope that in this case, I can kind of listen through several time steps at the same time. So for example, solves the problem of having to flip through images all the time. Although you can do that if you discover something, some kind of anomaly by listening, you can, for example, also flip through the time series, things like that. But what is perhaps what I'm a little bit more proud of is that in this newer version, you can do custom features and mappers. You can inherit from base classes and basically do whatever you want. Your feature extractor could be some embedding model, your synth could be Rave or whatever else, or any other classical DSP synth using the signal flow library in Python. And your mapper can similarly be anything you want. So in a way, it already transcends this original goal of implementing parameter mapping sonification. And why did I want to transcend it? Because as you know it much better than I do, there is an inherent problem with this approach of sonification, at least. While it can work for very simple things, just like think of the metal detector or the Geiger counter or heart rate monitor or things like that, like simple, like one feature mapped to one parameter, those usually seem to work. But as you add on parallel mappings of different features to different synth parameters, it starts to get a little bit murky, perceptually speaking. So there is this big question: how do synth parameters relate to the distribution in perceived sound? And you have done much more work in this, so I probably don't have to explain the problem to you. What I did is earlier on, some of you have also seen this in Oslo. I tried to relate the, you can see, yeah, you can see, distribution of synth parameters projected in a two-dimensional space to the distribution of various perceptually related representations. And I also did kind of interactive version of this. Again, sorry if this doesn't work. Oh, it kind of works. So in this map, you can, I guess the novelty in this was that it was quite snappy in term like compared to earlier attempts of making a thing like this. And so the idea is that you can qualitatively discover how your parameters relate to the perceptual distribution according to some kind of metric. This is, I think, based on encodec. Okay, so moving on. If this is the problem, one of my next ideas of how to solving it is something like this. What if we create some kind of idealized space for both the image features and then both the sound features, that is like latent variable models, some kind of latent space, and then do the mapping across the latent spaces. I know that this has a lot of assumptions. So, for example, is it even possible to create a unified space like that, perceptually speaking? Maybe not sure. And also, it requires that the distances measured in these spaces will be semantically relevant, which may or may not be the case. Hopefully, it is. So anyway, this is what I went with, and this is the model architecture I was trying to use. So I'm using the factor V architecture, which adds um, 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 adversarial component, trying to make decorrelated latent dimensions. So this is an attempt of disentangled representation learning. And so the idea is you train one on the images, one on sounds, and then you train a little mapper that tries to project relative distances from one place, one latent space to the other. And then at inference time, you can take an image, embed it into the image latent space, then project it, and then decode it as a sound. And to verify this, so far I did an experiment with what my opponent called the most over-engineered theremin in the world. So I took a toy image dataset with white squares moving left, right, up, and down as the only factors of variation, and a toy sound dataset of sine waves having varying pitch and loudness. And so the first task was whether the models find that these are really the underlying factors of variation. And they did a better extent, to a better extent for the images, but to a reasonable extent for the sine waves as well. And then the mapper model tried to um, match the relative distances while also with something called cycle constraints, find places in the target latent space which the target decoder knows well in a way. So sometimes you see on the edges it tries to create a little curvature just to conform better for the target decoder. And then the final idea is what I'm right now working on is how to scale this up. Obviously, this worked with this simple toy data set, or maybe not obviously, but perhaps obviously. But how do I scale this up to like very complex image data that I have to work with in the biology side, and maybe a more complex search space on the audio side as well? So for that, I'm now looking at actually adding instead of predicting spectrograms or even waveforms, predicting parameters, and then with the DDSP module, creating a synthesis. The original motivation for this was just better audio quality, but then I also get this added benefit of having a map between the let's say some kind of hopefully perceptually aligned distribution, but I haven't managed to confirm that yet, and the parameters. So that's really it so far, and I'm really happy to share this with you all. And I feel like a lot of what you're doing research is going to be very, very useful and inspiring for my continuing work. So yeah, thank you for your attention, and I take any questions.